Unit 5, you could label it as like interesting derivatives. So the first 2 lessons we'll do derivatives of implicit equations. Implicit differentiation just means derivatives of implicit equations. We've been dealing with explicit equations where you have y's in terms of x's. But lots of things in this world and universe cannot be expressed explicitly because explicit equations are all functions. They'd have to be expressed implicitly. I mean, you can have multiple equations to express this explicitly. You know, y equals plus or minus square root of 9 minus x squared. But it's easier to just write it down there. So this first lesson, we're going to take derivatives of something like this. It's an implicit equation. We'll be differentiating it. Implicit differentiation. Now, if you want to, explain what explicit is, y in terms of x.
Okay, if I go now and watch the video at home.
That's fine. Yeah, it's fine. It's up to you in this manner if you want to do it. We have explicit equations are typically functions. Plug in an x, you're only going to get one y. And the derivatives are easy. You take the derivative of this, you get dy dx is equal to 2x plus 2. Well, implicit equations have tangent slopes too. What does x squared plus y squared equal 9 look like anyways, right? It's a circle, exactly. You guys studied that last year. Well, circles have feelings. Sometimes they want to know what their horizontal tangent slopes are, so we can't forget about them. They want to know when they have horizontal tangents, they want to know what the tangent slopes of them are equal to 3 or stuff. We got to figure that out, okay? We can't forget about these guys, circles and other crazier shapes, okay? So we will take derivatives of this to do that. Now, typically these are not functions. And if I plug in an x, I'd have to do some work to get a y. And the derivative, we'll get to it. But let's go back to this one. When I ask you to take the derivative of this, what are we finding? Mr. Brewer, what are we finding? Yeah, we're finding y prime, which is the same as dy dx. They're interchangeable. Now, the way we did this, and it's important to write this down, is that we took the derivative of both sides, right? Usually, especially last unit, you didn't worry about this left side. You just went straight to the 2x plus 2, and then you set that equal to 0 to do a bunch of stuff. Well, you kind of skipped a step, and the step that you skipped was this piece over here. The derivative with respect to x of y, which is what we call y prime, or we call it dy dx. Now, how did I get that? I told you earlier in the year that this is kind of like multiplication. It's like d dx times y. There's a reason why we used this notation back in the day, because it's the instantaneous rate of change of whatever your variable is over the instantaneous change of x. The d ended up going with the y. The dx goes with the 1 that's underneath it. And boom, you get dy dx. This is essential to understanding how to take derivatives implicitly. That the derivative with respect to x of y is dy dx. Okay? Our goal is to take the derivative of this and find dy dx. Well, if I did that, the step would be this. Right? If I want to take the derivative of something, you take the derivative with respect to x of it. This would be 2x. Over here on the right side, the derivative of 9, what would that be? The problem is, what is this? Right? dy squared over dx is a great guess. Maybe it's dy with another y. Let's figure that out. Okay? We're going to skip this, go straight to here. Taking derivatives of other variables with respect to x. Let's do quickly the derivative with respect to x of y. If you haven't written it down yet, write it down again. We know that's dy dx. Well, let's do that y squared. Well, all the information I'm kind of given that I know is this. Right? So, since I know this, what I'm going to do here is make this like a chain rule problem. I'm going to put parentheses around that y and make this a something squared on the outside, and then the y on my inside. So if I wanted to take the derivative of y squared using the chain rule, I would take the derivative of the outside, leave the inside alone. So that's the derivative of the outside, leave the inside alone, then multiply it by the derivative of the inside. Well, if the inside is y, what is the derivative of the inside? dy dx. The derivative of y squared with respect to x is 2y dy dx.
Would that be simplified to 2 dy squared or no?
Yes. I'm going to go ahead and say yes. Would we want to do that? No. Because what we're ending up trying to find here is the slope of the tangent. Slope of the tangent is our instantaneous change of our y's over the instantaneous change of our x's, right? Slope formula, change in y's over change in x's. If I wanted to find the instantaneous change of my y squareds over the instantaneous change of my x's, I could by doing that. But eventually our end game is to find just this. Okay? So let's go back up here. I'd have 2y dy dx, but I would not say this is my derivative. Let me get rid of this stuff. This is not my derivative. I'm looking to find what dy dx is by itself. Just like in my explicit equation, I found dy dx was equal to 2x plus 2. And it's an equation that told me the slopes of my tangents of y, the instantaneous change in y's over the instantaneous change in x's. What I would do here is just do a couple extra steps to find out that dy over dx was equal to negative 2x over 2y, which is just negative x over y. How do I do that? Subtract 2x from both sides, divide by 2y. I solved algebraically to find dy dx. Now, we'll practice this more because we need to talk about the derivatives of y's, but right now we're just talking about an implicit derivative. This is an implicit derivative. We differentiated an implicit equation. We got an implicit derivative. This is still a tangent slope generator. For x squared plus y squared is equal to 9. Just like for this equation, this is our tangent slope generator for x squared plus 2x plus 3. However, for this guy, I plugged in x and I got a slope, a tangent slope. For this guy, what do I have to do to get a tangent slope? I got to plug in an x and a y at the same time. So it's a little more difficult. I have to plug in a point to find a tangent slope. Well, I mean, let's find a couple tangent slopes to this nice little circle. Somebody tell me a point that's on this circle. 3, 0. Well, dy dx at the point 3, 0 would be negative 3 over 0. What's that? Undefined, right? What does it mean to be undefined if I'm rising 3 and running 0? Vertical. Oh, if I go into my graph, I look at the point 3, 0. Look, we got a vertical tangent right here. I could look at the slope at 0, 3. I plug in 0 for x, 3 for y. I get 0. I notice at 0, 3 on the graph of my function, I have a horizontal tangent. Okay? And all these other points, you'd be able to plug in those points once you found the points to find the slopes of the tangents. Okay? That's the end goal of today. Take derivatives implicitly of these implicit equations, and then we'd be able to plug in points to find the tangent slopes. So we did y squared, 2y dy dx. What if I asked you to take the derivative of 3y cubed? Well, I can think about it like a chain. 3 stuff cubed on the outside, a y on the inside. I could take the derivative of the outside, leave the inside, times the derivative of the inside. 9y squared times dy dx. Let's try cosine y. Well, you can write it as cosine of y you can use the chain rule to take the derivative of the outside, leave the inside, then to take the derivative of the inside. Outside is cosine, the inside is y. What do I get? Good. Negative sine y times dy dx. Well, what do we kind of notice after doing this chain rule kind of procedure a couple times? Volunteers, Mr. Tabbitt?
You always end up with dy over dx.
Yeah, we always end up with a dy over dx at the end. And what about in the beginning? Yes, Mr. Wusu, it's generally the same. It's the same exact thing as the derivative using x's, except we just add a dy dx at the end. Okay? So if you just remember that, you're okay. Just take the derivatives the same way. With a dy dx being multiplied at the end. Okay, one more with just y's, and then we'll talk about stuff with x's and y's. So do that one, sine of y cubed. Sharpening up our chain rule. We kind of didn't have many chain rule problems last unit. Well, it's back. Cosine is the derivative of the outside. Leave the inside. 3y squared would be the derivative of the next piece. Dy dx would be the derivative of the last piece. Now, just to show you, but not to confuse you, I'm not even going to do this. I could do the same thing when I take the derivative of like 3x cubed. I could use the chain rule procedure to say this is 9x squared, and then times the derivative of x, which is 1. Or I could say the derivative of x with respect to x is dx over dx. And I could have put dx's over dx's every single time when I'm taking a derivative normally. Okay? But we know that this is just 1, which is why we exclude it when we're taking the derivative and our variables are aligned. Okay? So we could have had these guys at the end of all of our derivatives if we wanted to, but it just was not necessary to show, and it's redundant. So we do have to do it now since it's not redundant. All right. Well, I can have x's and y's. First guy's a piece of cake. Because you know when we're adding things together, you just need to take the derivatives of the individual pieces and add those together. So, it's more, what's the derivative of y squared? With a at the end. And then, Mr. Brewer, what about the derivative of x squared? That's it. Piece of cake. Everybody can do that. No problem. But it's when we have something like this, the derivative of x squared, y squared, that's where people start making mistakes. Because a lot of people forget what crucial thing to take the derivative of x squared, y squared? Product rule. So, don't forget your rules if you're dealing with more than one variable. They still apply. I would treat this as a product, and I'd use the product rule to find its derivative. So we get f prime, so the derivative of the first times my second. No dy dx is here. I'm not taking the derivative of the y squared. I'll add the derivative of the second, which would be 2y dy dx, times the first. That's it. If you wanted to reorder this so that it's 2xy squared plus 2x squared y, then a dy dx, you could do that. But it's not necessary. You're good. As long as you do that one. Now these are just derivatives of expressions with multiple variables. The goal is to take these expressions, put them into equations, take the derivative of those implicit equations. So x over y. Any questions so far? Well, yeah. If I told you to take the derivative of this, you do it like this. In the future, we're not going to leave stuff like this when we're taking the derivative of equations. Let's try one more, make sure we have this one down, and then we're good to continue and take more derivatives. X squared plus xy plus y squared. Product. Most mistakes happen in the middle. this is a product of x and y. If you wanted to take the derivative of this in the middle, you have to use the product rule. The derivative of all the other pieces are straightforward. You have 2x at the end, we'd have a 2y dy dx, but the middle would be f prime g plus g prime f, and then the derivative of y squared 2y dy dx. Okay, so all those terms. Questions? All right, well now let's go for it. Implicitly differentiates. Make sure you take the derivative with respect to x of both sides of an equation, and then all the other stuff, which is just help, is just solve for dy dx. That's all this stuff in the middle. But typically, in most of the implicit equations, you solve by having to move all the dy dx terms onto one side, move all your other terms onto the other side. You'll factor out a dy dx. You'll end up solving by dividing, and I'll show you exactly what that'll look like. Stay with me, Mr. Robertson. There you are. Okay, really it's just two steps. Take the derivative and then solve for dy dx. However, it's solving for dy dx that people have problems once our implicit equations get more difficult. All right, so this equation again, now that you kind of done the steps, we can do it again a little easier. Take the derivative of both sides. I don't know if this is completely proper. Usually it's both, but I mean, it's fine. Like solving equations, you could do this as well. 3 times everything. So we'd get 2x, 2y dy dx equals 0. Step 2, solve for dy dx. How do you do it? Move the terms without the dy dx out by subtracting or adding. Leave all the other terms with dy dx's on one side. And then we solve by dividing. This one is easy. There's not much of the solving step that you have to do, but I will show you it gets more difficult. And you'll need lots of paper to do these. Okay, so let's look at that one. This one, not that bad, but a good example of having to move stuff with dy dx's on the one side and leaving them on the other. One third y cubed plus 2y squared minus 5y minus x squared equals -4. Let you get that down. and then we'll get going. Step 1, differentiate both sides with respect to x. One-third times 3 is just 1. I get y squared dy dx plus 4y dy dx minus 5 dy dx minus 2x equals 0.
Wait, so when the 5y, you wouldn't just take out the 5. Oh, wait. It wouldn't just be negative 5, I guess. Like it is 1 with x.
Good. That's a good question. Ran into this problem last class too. The derivative of negative 5y. So if you take the derivative of negative 5x, right, it's just negative 5. Well, it's negative 5 times dx dx. It's the constant times the derivative of the variable. Well, I can take that as well. The derivative with respect to x of negative 5y would be the constant times the derivative with respect to x of y, which is dy dx. So just like how we did 3y cubed, we got 9y squared dy dx. Okay, so now that we have this, we need to solve for dy dx. That's what I'm trying to find. I'm trying to find my derivative, what my instantaneous rates of change are. I need some sort of equation, whether it's implicit or explicit, so that I can plug in points to find slopes of tangents. How we'll do that? Move the stuff without dy dx's onto one side. Leave all the stuff with dy dx's on the other. Factor a dy dx. All of these terms share a dy dx that you can factor out. So if I pull dy dx out of my first guy, I'm just left with the y squared. If I pull them out of the second guy, just 4y. Pull it out of the third guy, I'm just left with 5. Well, last step is that this is a product. To solve for dy dx, we would divide all of both sides by this guy that I wish to remove. And after all that, I get my derivative. My tangent slope generator, where I would plug in points on my equation, and I'd get slopes of tangents. Mr. Jesperson.
Will it always end up being x terms or y terms?
No. So let's try another one. Good lead-in example for that question. This is a truncated ellipse. I don't know if that's the correct word. It's a shifted ellipse, rotated a little bit. Don't forget the product rule for your middle terms. And don't forget to take the derivative of that 10 on that right side, which is 0. Okay. Get all your dy dx's on one side, get all your other terms on the other side. Using algebra, we're adding or we're subtracting. In this case, we're subtracting. Factor. And then solve. Now, our derivatives end up like looking interesting, right? It's like the same thing, but kind of flip-flop. It's almost elegant, and it almost should make sense to you why it ends up being like this. And it has to deal with the pictures of these graphs. So x squared plus xy plus y squared equals 10. Is this kind of rotated ellipse. And you should kind of see the symmetry in the ellipse. And the symmetry that occurs in the ellipse also corresponds with like the symmetry in the tangents. Like a tangent here would be the same as the tangent here. Tangent here would be opposite the tangent here. Tangent here is the same as the tangent here. So that's why you get these really like interesting looking guys that, you know, it's almost the same stuff on the top and the bottom. Maybe they're opposites. Maybe we have y's instead of x's. But don't be afraid if you get this. This is good. Okay, now we will have x's and y's on both sides of the equation. I believe this is some sort of like curly Q. X cubed plus y cubed is equal to 7xy. Yeah, looks like that. So we can find the slopes of the tangents of that type of curve. So it's a good question. You can leave the 7 out, but it makes things difficult when you're solving for dy dx. So I would recommend you put it with the x and make this 7x times y. Okay, before you do too much work, let's just make sure we have the first step right. If you left the 7 out, and if you have parentheses, it's difficult to manipulate an equation and isolate certain things if you have parentheses in it. Like all I could do right now to get rid of this dy dx and move it to this left side would be to divide by this entire thing. But that also moves my y over there to the left side. So I don't want to do that. If you ever see parentheses in an implicit derivative, get rid of them. They're only going to cause problems. So if you left the 7 out, first thing you should have done was to distribute it in. If you did not distribute it in, but you just took the derivative of 7x times y, then it would have already been distributed. So what's going to be easy to work with is going to be f prime g plus g prime f, which is really the same deal. Now, moving your stuff around, I'd subtract the 3x squared to move it onto the right side. I'd also subtract the 7x dy dx. You can move the 7x to be in front of the dy dx if you want. So you get 3y squared dy dx minus 7x dy dx equals 7y minus 3x squared. Then you factor out and you solve. That's annoying. Okay. What's up? Oh, yeah. So some of you might have brought these dy dx's over to the right side, moved the other stuff to the other side, and you would have gotten the following: negative 7y plus 3x squared over negative 3y squared plus 7x. Is that right? Yeah, so that's just factoring out a negative 1 from the top and the bottom and just canceling them. Completely the same thing, just looks different. So if you have opposites of everything, that's fine as well. But if you have something that's not an opposite in the right way, it's wrong. Okay. Now, I'm not going to want you to do this one like I read it. But I'm just going to want you to write this one down in case you encounter something like it on your homework. Okay, 3 times x squared plus y squared squared equals 100xy. And don't start. I'll show you why. This will be tough to simplify. 6 x squared plus y squared to the first times the quantity of 2x plus 2y dy dx, which equals 100y plus 100x dy dx. This piece right here you cannot remove this dy dx unless the parentheses are gone. Or you can't move the 2x to put the 2x onto the right side unless those parentheses are gone. I can't just subtract 2x on both sides. No. Where it's in parentheses, it's being multiplied by something, order of operations, I'd have to do those multiplication inside those parentheses first. How could I get around that? Yeah, if I divided the 6x squared y squared onto the right side, well then the dy dx is stuck in a fraction. The only way to get rid of this problem is to distribute everything. I don't want to distribute this. Instead, I could have distributed this. First. The chain rule is kind of like the death of implicit differentiation. It's where you get parentheses and where you get stuck. So before you use the chain rule, try to see if you can't simplify stuff so that you don't use it. So I'd get x to the fourth plus 2x squared y squared plus y to the fourth, which is equal to 10xy or 100xy. And then you can distribute the 3. And then after you have stuff all being added, no longer do we have chain rule stuff. This is what we would take the derivative of. I don't want you to do it because it'll just take us a little. I miss a lot of 3s. Yeah. Sorry. Okay. You take the derivative of that implicitly, and then you would solve for dy dx. So maybe let's do this one. Find the slope of the tangent of sine x plus 2 cos 2y, which is equal to 1. I don't even know what this looks like. This could be interesting. So we could have trig functions in our implicit equations. Okay. You just finish right here. Yeah, that's okay. Let me graph this. See if I can copy. Whoa. A bunch of fishes. But they keep going, I'm sure, forever. But that's neat.
So are the parentheses on that input correct?
Yes, exactly. It'd be cosine of 2y, not the cosine of 2 times y. Okay, and now, once we get our implicit derivative, we can plug in that point, 0 pi over 6. Yep, to find our slope of our tangent. So go ahead and do that. I'll do it, and we'll see if we get the same answers. 1 over 2 root 3? No? Ugh. 1 over 2 root 3? Thanks, Jake. Derivative of sine cosine. Derivative of 2 cosine 2y would have been derivative of cosine negative sine. So negative 2 sine, leave the inside, times the derivative of the inside. The derivative of 2y is 2 dy dx equals 0. Subtract the cosine, then divide by the negative 4 sine 2y. How did I get the negative 4? I got this 2 and this 2. Cool. Cancel the negatives. You get that guy. Then find the derivative at 0 pi over 6. Cosine is 0. I'm plugging in 0 for x. I'm plugging in pi over 6 for y. We get 1. And then sine of pi over 3 is root 3 over 2. 4 times root 3 over 2 is 2 root 3, so you get 1 over 2 root 3. 1 over 2 root 3 is approximately a small number. .288, so that's like a quarter. So at 0, the slope here is 1/4 approximately. That looks about right. Now we do have this negative slope as well. It's kind of making me think that those negative answers that you got might be right as well. Did anybody get negative 1 over 2 root 3? And see if, did they do any mistakes, or you just do it a different way?
Well, I made a mistake. I didn't, when I was doing cosine to sine, I didn't make it a negative, so.
Okay, so maybe the graph we're seeing is not the correct graph. That might be the case. All right, so that's it. That's good. We just found the slope of a tangent to an implicit equation. Well, we will be asked to find the locations of horizontal tangents to implicit equations. Like that one. But we know through practice that we just need to take the derivative and set it equal to 0 and solve. Let's see if we can do that. Most common mistakes made are people, after they kind of done a couple of these, they start skipping steps and they start just moving stuff instead of doing all of the algebra. And when they factor, they miss stuff. So be diligent, be careful, do every single step, and you'll be okay. Okay, I got this, or you can get the opposite of everything. Well, question was to find the xy locations of the horizontal tangents. So set this derivative equal to 0. How do I solve this? Not the denominator, the numerator. Numerator. If I have a fraction set equal to 0, I'm just concerned with the numerator set equal to 0. And we find the x location. Well, I'm asked for the x, y locations. What do I have to do? Plug it into my original, and what used to be simple no longer is. Now I have this guy that I have to solve. Ends up being not that bad. 4 minus 8 plus 4, you get y squared plus 4y equals 0. Factor out a y, you get y is equal to 0 and negative 4. So let me just show that. Getting you your points. 1, 0, and 1, negative 4. Turns out this guy looks like an ellipse. If I graphed it, we would see that. Now, if I asked you for the locations of the vertical tangents, what I would do is I would take this denominator and set that equal to 0. I'd see when this was undefined or when your denominator is equal to 0. So don't forget that. If you're finding vertical tangents, it's like finding, your critical points when you're setting your denominator equal to 0. In this case, you're doing it to find locations of your vertical tangents, which was, possible situations. And you take that negative 2, plug it back in. Now, let's talk about some tough ones. Horizontal tangents for this one. And kind of breeze through it. If you just want to watch, that's probably okay. Take the derivative of this, but make sure you're paying attention, not making too much noise. 3x squared plus 3y squared equals f prime g plus g prime f. Subtract, solve, I'd get dy dx is equal to 6y minus 3x squared. This is dy dx here. I got it. This is why you got to be careful, guys. Gosh. Over 3y squared minus 6x. Okay? Well, a horizontal tangent would occur when the numerator is equal to 0. Well, I get 6y minus 3x squared is equal to 0. I can't solve this to find an x or a y. But what I can do is set up a system by adding 3x squared and subtracting, dividing by 6, where I'd get what y was equal to. Y is equal to 1/2 x squared. Well, how does that help me? I'm trying to find locations, x, y locations of my horizontal tangents. You would take this y, which is equal to that, plug it back into your original equation, and solve that, which I'll do, and it'll be on your video. Okay. So how will this look? Well, in my original equation, I'd have x cubed plus, wherever I see a y, I have a 1/2 x squared. So it becomes 1/2 x squared cubed, which is equal to 6x 1/2 x squared. Now that we have just one equation, one unknown, we'd be able to solve, hopefully by hand, but if not, we could have a calculator question like this. I believe we can do this by hand. I can subtract the 3x cubes to both sides, giving me negative 2x cubes plus 1/8 x to the 6th equals 0. So to solve something set equal to 0, factor to make a product, and then we find when the individual pieces equal 0. This will occur when x is 0, that's the first piece. Now we have to solve this guy. I would add 2, then multiply by 8. And then I would take the cubed root. It's not a nice number, but it's a number that we can find nonetheless. It's approximately 2.52. And those would be the x locations. To find the y locations, I'd have to take those values and plug it back in here. Again, would not be great. Probably we'd have to solve those by using our calculator. But let's just go ahead and just end it here with these x coordinates that we could find. And then let's just check the graph of this. X cubed plus y cubed equals 6xy. I believe it's one of those curly Q guys. X cubed plus y cubed equals 6xy. And we're looking for horizontal tangents at 0 and around 2.52. Once my computer starts working. There we go. Here's that curly Q at 0 right there. It looks like we have a horizontal tangent. And then at 2.5, right around up here, looks like we have a horizontal tangent as well. So we succeeded. We found those locations of those horizontal tangents. But of course, it's a little more involved because we have to set our derivative equal to 0, set your numerator equal to 0, and then once we get this, we need to isolate a variable to plug in here. So don't forget that. Good luck on your homework.